I'll just welcome everyone to session 9 of Decarb Debrief, and also Happy Engineers Week. Wendy and Martha and I are deep into creating our little thing out of popsicle sticks and matchsticks and everything. So you've got some stiff competition from the Wild West out here. So for those of you who don't know me, my name is Alex Sherf. I'm the Sustainability Program Coordinator, and I'm filling in today for Wendy Placco, who could not be here. So Decarb Debrief is a monthly webinar series designed to increase knowledge firm-wide. And if you have a topic that you'd like to see, we're always looking for new ideas, so send them our way. So today's topic is a case study on the University of Massachusetts Amherst campus and their decarb efforts. And we have Bill Mahoney and Eric Chrencik here to share their strategy and some lessons learned. So Bill, I'll have you introduce yourself first, and then Eric will take it away.
Okay, Bill Mahoney in the Baltimore office, and Eric and I work in the chilled water group here in the infrastructure side of the business.
All right, first things first, you're going to be sharing then for us, and we jump right into it. First slide. All right. Yeah, Eric Chrencik, mechanical engineer and project manager, running the chilled water group out of Baltimore with Bill. Perfect. Yeah, so I'll be jumping in to basically give everyone a little tour and adventure through what we've been doing at UMass Amherst for, at this point, it's been over 10 years. Hit the next one, Alex. Let's see where we are. So it is their flagship campus. It's the Massachusetts flagship campus in Amherst. So many power plants, a couple chilled water plants, a lot of buildings work. And hit the next one here, Alex. This will really tell how we've supported UMass and how the campus itself has evolved and how we've helped evolve it over time. So starting back in 2014, it started with Andy Jones and the master planning group with a master plan, which then led to the chiller plant. It was commonly referred to as the polymer plant, and we renamed it the North plant. So that was a 6,000 ton chiller plant that we constructed on campus. That included us in Baltimore in the chill water group. It included electrical. It included actually our Ohio Civil Division. We had an architect, and it was the full thing, soups and nuts, building the entire chiller plant. In 18 and 19, we had some building energy conservation projects. The STEAM group chipped in with a ton of manhole surveys, steam and condensate piping designs. Working our way to 2020, thermal energy storage tank study. In between there, by 22, they launched their carbon initiative, their net zero initiative, which we were successful in achieving, which is part of their proof of concept planning that we developed for them. And then with that, as that moved forward, we continued to evaluate thermal storage. And right now we have a thermal storage tank under construction at the university adjacent to the North Chiller plant.
Yeah, thanks, Eric. And what I find really interesting that's worth mentioning for our listeners today is that this project touches on nearly every single division, practice area at our firm. So I just think that that's really interesting. And I'll let you just continue going on with plant history.
Yeah, that's perfect. Exactly it. And then the plant itself, old steam plants where they started, they operated a coal plant for almost 100 years at the university. And then in the early 2000s, they constructed their CHP plant, which won many awards. And it's actually a very beautiful building with all glass seen on the right there. However, they have decided that it's time to move on from their combustion turbine plant, and they're moving towards the net zero world. That's part of their goal. And they understand that this was a stepping stone for themselves with their CHP plant, but they're looking at alternatives moving forward into the future to get off their steam system. That said, they actually have a ton of solar power there. They're heavily invested in getting to all renewable energy in a very short period of time, less than 10 years away by 2032. And they've committed large investments. And then the key to what the university was trying to achieve, as well as a bunch of other universities too, right? There's some low-hanging fruit, such as looking at renewable energy sources, but with so much of the energy usage on campus being via heating and cooling sources and means, they were really looking at how they can balance their energy and trade that energy. So whether it was ground source heat exchangers or moving to some low temperature hot water systems. That's what you see reflected in the red. And that's where they were really trying to chip away at their greenhouse gas emissions. And that's really how the proof of concept study that we prepared ended up being formulated. And as we talk about trading heat, it's some more broader concepts. Part of what we were looking at and proposed was converting to hot water away from their steam system, with the idea that they could use heat recovery chillers, they could operate at lower water temperatures to have some reduced energy losses throughout their systems, and then really take advantage of simultaneous heating and cooling, which also paired with ground source heat exchange can give it a lot of flexibility in modes of operation and really hit hard on the electrification piece. And then with ground source heat exchangers, the two main items we were looking at both vertical and horizontal. They actually have really good ground properties around the university, which really made just vertical heat exchangers almost like a slam dunk when comparing the two. And we'll get into that a little bit too. We had some test bores that we performed up there, gave us some really good understanding of thermal performance in the ground.
Thanks, Eric, for that overview. So let's switch gears a little bit and talk through the strategy that helped UMass achieve its significant goal of carbon neutrality. Bill, can you talk us through that?
Sure. They hired us, as Eric said, a few years ago, 2022 or 21, to do what they called a proof of concept phase 1. So they had that high level 40,000 foot overview that said, locally source your food in the kitchens and put in solar power and things like that. But the big target was the central heating system. And so they said, let's do a proof of concept. We won't try to convert the whole campus. Let's pick this quarter or to a third of the campus, which is this area down here, you can see, and we'll just convert that. They thought it was a good idea because it's near the central heating plant there, which is right there, and that's where all the steam comes from if we needed to pick up steam or for supplemental heat. We had I think they chose this area because this is called Boyden Athletic Field here, and that was our bore field. So we ended up with a 750 bore heat exchanger in that intramural field, and so it was pretty much ours. We had to phase the work so they could keep using some of it all the time, but it was a wide open field for us to do our bores. Turns out it was actually kind of limited, not quite enough for us to do all the full load we needed to. Other problems with the areas that they selected here, there's an honors college, the red buildings, that's relatively new, heated and air conditioned, nice dorms. There was the Boyden gym, and there were a few other cats and dogs in there that were a couple of academic buildings, but very few. And then the majority of it was the Southwest resident area. It's these big, brutalist, 20-some story high-rise dorms, 1960s and 70s construction, bad windows, not much insulation, and no air conditioning. So heated only. So when we've talked about this in these other decarb debriefs, the Northeast it's tough for a ground source heat exchanger system, which is what they wanted us to do here, if that wasn't clear. It's tough in the Northeast because there's a climatic imbalance. Your energy that for the heating system over the course of the year will require more BTUs than the BTUs that your cooling system for a given amount of buildings heated and cooled will put into the ground in the summertime. So that's always going to be an issue in New England. Maybe jump to the next slide. Our issue was heightened here because so many of the buildings weren't air conditioned. So they have even less air conditioning relative to the heating load than you'd expect for a New England facility. So this is the profile. You've seen these in these other seminars. Heating is the reddish stuff to the top, and cooling is the blue stuff pointing down. And in the summer, you see the cooling pick up, and the winter on either ends is the heating load. So this was the profile of how we dispatch the equipment that we were recommending, which included mostly ground source heat exchangers, but we also had backup because they couldn't do the whole load. We had backup from potentially using some of the steam in a heat exchanger that's there available from the cogen plant. We also looked at condensing gas boilers, and we looked at air source heat pumps. So the way this profile breaks down, first you would do simultaneous heating and cooling. That's all the purple in the middle here. And there's not a whole lot of that. But the heat recovery chillers would do our simultaneous heating and cooling. That's our highest COP, 7 or so for that. And then beyond that, in the summertime, if you needed more cooling, then you would use the ground water. It's labeled here as water source heat pump cooling. That's this light blue area here, and that's cooling from the ground. So you're basically storing the heat in the ground, and then in the wintertime, we're going to pull that out. That's this salmon colored. So this cooling that we stored becomes this heating that we pull out of the ground in the fall, and then into we ran it all the way through the winter almost. So that's the use of the water source, ground source, geo-exchange heating system. And then we filled in some blanks here since like we said, we've got a given amount of cooling that we were able to store. We only get that much heating back out. So we have to make up the difference. And that is first made up with air source heat pumps, which is the green areas here, right in the shoulders of the heating to cooling season. We intentionally run in that period because that's when the ambient temperatures won't be so cold. So we can make our design temperature for the hot water supply going out to the campus. And it's a pretty good COP if it's only 20, 30 degrees outside. And then in the dead of winter, we just can't do it all. And we're left with these big areas here of the dark red, and that's just the supplemental heat. That's the original cogen steam or condensing boilers, electric boiler we looked at that ended up being against the code up there in Massachusetts. But that's where they were at. And I don't know if we stated this or not as far as the code goes, but ahead of the code, they have a executive order, so a mandate for the whole Commonwealth up there. And so any state building can't be served with any sort of a fossil fuel. So even though they had this large cogen plant, they couldn't put any new buildings onto this. So they had a real predicament here to deal with. I guess move on to the next slide here.
Yeah, Bill, I had a quick question. You mentioned COP and a COP of 7 for the simultaneous heating and cooling. What does COP stand for again, and how does that relate to the other technologies you mentioned?
So coefficient of performance, and so to throw on the numbers, it's a ratio of how much energy you put in. These are all compressorized. How much electric energy I put into the compressor versus how much useful heat energy I get out in a heating COP, how much useful cooling I get out in an air conditioner, a chiller or something like that. And then, for instance, the purple, I'm putting a kW into the compressor, and I'm getting out useful heat and useful cooling, and therefore the COP gets up to like in the 6 and 7 range for that. Some of these other ones, the salmon heating from the ground, that's 3. And so that's what you get. That's kW out versus kW in. As opposed to the efficiency, we have these boilers here in the red. They've got an efficiency, if we're using their steam system, of probably like 80%. So that's for every kW BTU we put in, we only get 80% of the BTUs out.
So it's really
energy-wise, dollars is a different story because the energy costs more for electrical. But as far as energy in versus energy out, you're getting multiples better with these compressorized heat pumps, air source heat pumps, ground water source heat pumps.
So it's good to do the simultaneous heating and cooling. Can you tell us a little bit more about why they're not doing it more simultaneous?
You can only do what's there at the time. You've literally got to have simultaneous. It's got to be this hour of this day. I've got this much heating load, therefore I can get that much simultaneous cooling load also, but I can't do any more. Otherwise, I've got to have somewhere else to put the heat in the ground for instance, for the light blue cooling system.
That makes a lot of sense.
So
Thanks.
we do have one caveat on that, and we're going to get to that. But there's a thermal storage system here which helps us with that simultaneous. You can shift the simultaneous loads a little bit because they have thermal storage here coming on. But just going back to the balance. So again, we've got this ground source heat exchanger, and like I said, we want to in the summertime, we're going to put heat into the ground, and in the wintertime, we're going to extract the same heat back out of the ground. Now, this is just looking at the phase one, so it's just a quarter of the campus, and how much annual heating and cooling the buildings need. Forget about the system, but the buildings require, it was that kind of a 4-to-1 balance, a 3-to-1 balance. So a quarter of the annual energy was used for cooling, 3/4 for heating for our mix of buildings with all those high residential buildings, heating only, right? Next slide shows you that if we looked at the overall campus where you get some big labs, a lot more cooling spaces, most of the places are air conditioned up there outside of the buildings we were looking at, it's closer to a 2-to-1 ratio. So 1/3 is the cooling annual energy, and 2/3 of the heat makes it up. And then the next slide tells us that when we get to the overall campus, which ultimately they want to expand the whole system to serve the whole campus, it's really not that bad where we have to have a complete 50-50 pairing. Because if you think of what's happening in the summertime, I've got a building load here. I've got to put those ton hours into the ground, right? But I'm also putting in this light blue is the compressor heat. So whatever my COP is, I've got, let's say I get 3 useful units that I put into the ground, but I also put the compressor heat into the ground, so that puts 4 units into the ground. And so it helps you. It stores more heat in the summer that you can use in the winter. And then kind of the opposite way, in the winter, I might have a load that's this whole 2/3 of this pie, but I only need to get this portion out of the pie, out of the ground, because this portion, the light one here, is the compressor energy that we're going to put into our heat recovery chiller. And so that also gets used as beneficial heat. So this kind of this is a balanced system is what the point of this slide is. Even though the cooling doesn't have to, the load on the building cooling annual basis does not have to equal the annual energy load of heating. It's just got to be close, but you make up the difference with these compressor energies that help you in the summer and in the winter because of the direction the heat's flowing. If that makes sense. Next slide. And then this goes to show you, like we said, a good portion of those high rises didn't have air conditioning. So we laid out what we could do with our 750 bores to support ground source heating and cooling. And we could only serve what the air conditioning load was. So their load was only this darker blue here in phase one today. If they went and added the cooling to the residences that don't have it, we would get up to this point. But even still, that's the load the buildings required. What can our system produce? Our 750 wells would only produce this much cooling as a peak. Now we're talking about instantaneous capacity. We're not talking about the annual BTUs. We're talking about MVH, instantaneous, tons, kW, instantaneous capacity. What we need to do then to meet our load, this wouldn't even meet our peak cooling load today. We needed to add some supplemental cooling for the phase one work, and then follow-on work. Once this cooling gets added, we need to add more capacity in more supplemental. So what this told us was even that big athletic field that was available to us, it looks relatively big, it still wasn't enough to meet the current load and nowhere near enough to meet the load if all those buildings were air conditioned. And then the same thing happens here on the heating side. I've got it juxtaposed here, but there's your ground source. The brown is the ground source, and that can't meet the this whole building load that's required in the winter. So we had to do this supplemental heating, which is this guy. And we provide that, like we said, with condensing boilers or steam heat exchangers, or uh, then the option on top of that was it wouldn't serve you in the middle of the winter, but in the fall and spring shoulder periods, we have air source heat pumps to kind of supplement some of this boiler operation. And that's another, emission-free, scope one emission-free heating method. So that's the mix of what we had recommended to them for their plant capacity.
So I know a lot of these campuses, Bill, are going to low temp hot water. What did you choose for the UMass Amherst system, and kind of why? Can you talk us through that a little bit?
Just this is a quick slide that summarizes what we looked at there. First option was 120 hot water supply and 100 return. And the second option we compared was 140 supply and 110 return. And there's reasons to go one way or the other. Martha was always pushing for the 120 because if this supply temperature is the key to what kind of equipment you can use and what its COP is. So there's no question dropping the supply temperature from 140 to 120 definitely helped our COP. We're definitely going to use less energy day after day. The other difference here was if we did raise it up to 140, we felt we could tolerate a temperature drop of 30 degrees instead of 20 degrees, take it down to 110. So that ended up being a big deciding factor. So the chart here on the right shows you that this is the 120 column on the left, 140 on the right. And you can see in green that the electric energy is definitely higher for 140. This is life cycle cost. This is 25-year life cycle cost. So yes, I'm going to pay more every hour, but in 25 years, here's what it relatively adds up to. The next tier here is the gas usage, and that's kind of a wash. You're going to get a little more capacity probably out of the 120 system. So this column might be a little bit shorter, but they're pretty equivalent. The big driver here into which way to go in the life cycle cost analysis was the pink up here, and that was the marginal capital cost, not the total capital cost, which were a lot more, but just in marginal capital cost. How big? I think the pipe sizes went from 24 to 18 inches for the heating water supply, and we ran a lot of piping in our analysis. And that was worth, you can see here, $5 or so million, and that's the driver. So you're saving maybe $1 million here and there in the energy cost, but that capital cost was the driver.
Great. And so let's talk a little bit about the technology then that you recommended.
Yeah. Next slide. All right. Eric, you want to cover this one?
Yeah, I'll pick it up. So that was one of the items. It was kind of where we started, right? What's even out there? We were foraying into something that's a little nuanced and different to us in a sense. While a heat recovery chiller in itself may not have been, because we had a couple installed, it was what manufacturers can meet what hot water supply temperatures, what capacities can you get to, and we developed a graph you see on the left side of the screen here, where we looked at plotting just capacities and temperatures and where things shook out. And for the most part, multiple manufacturers could get to that 130, 140 degree hot water supply temp, although capacity was generally limited. However, that's not the worst thing at the end of the day, because as we're continuing to find out, sometimes multiple compressors give you greater turn down, which at the end of the day, having a unit or multiple machines that can achieve high turn down can really help you when you do have some low load conditions. As Bill was showing on his graph earlier, there were times where the cooling load was almost nothing at all. So there's times where you do need a piece of equipment that can really get you down into a lower load condition. So we built this in 2022. And then over the course of the last 2 to 3 years, just from some designs we've had and continuing research of the red line in and of itself isn't quite right on here. York CYK machines, the 400-ton model can get you 170 degrees, and then between 600 tons and like 1,000 to 1,200, you can only get 155. And then once you pop over 1,500 tons, you can get back to 170 again. And so there's little things like that are quite odd. And it just is what it is what I get from York when I talk to them about it. Just that's what the machines can do, and that's what they've tested and have proven out. They also have a screw machine with its 200 tonner nominal with duplex screw compressors, and that can get you effectively a 4-to-1 turn down, shut a compressor off and ramp one of them down to 50%. That can get you 176 degrees, I think, peaking out. And then you got some other guys like Oilon has a screw machine, duplex screw, same thing, but they get 160. They have a piston machine that's little 10-ton modules, and that can get you 180 degrees. And all this that I'm saying in temperature wise, that's simultaneous with 42-degree chill water coming out too. So we're talking 42-degree chill water with 170 to 180 degree hot water. And then you even have some natural refrigerants in the mix where you're talking ammonia, for example, like GEA. They have two options, piston and screw machines that can take you up to 180 degrees or so and up to about the 500 ton range. So we're continuing to develop our knowledge on this and continuing to document what's available and out there. And it's changing. I don't want to say quite day by day, but it's almost day by day. We had, who was it, Bill, that came in? It was multi-stacks guys like Buzzard or whatever their name is. Some other guys, they do custom fabricated machines they do screw type machines. I was looking at them at the University of Albany as an option. And they're doing the same thing where you get 170 plus degree hot water and 42 degree chilled water. So continuing to evolve is the big takeaway.
Yeah, that's really interesting. And this next one I'm particularly curious about because I always thought air source heat pumps were just not practical. As living in Minnesota, I mean, even in February here, we've had 12 days out of the 20 so far this month that have been sub-zero. Even when I drove in today, it was -1, and that was the temperature, -25 as the wind chill. And so I thought that they really didn't work in super cold temperatures. So can you talk me through why air source heat pumps were useful for UMass Amherst?
Yeah, hit the next slide. And same thing here. This continues to evolve. You can get 2-pipe type and 4-pipe type, right? So 2 pipes coming out or 4 pipes coming out, and you can get like 5 modes of operation, right? Like heavier heating, heavier cooling, while simultaneously doing the load. All heating or all cooling and using the air as your source, or just full simultaneous 100% loaded up. And so with these, we've looked at big farms or fields of air source heat pumps, and then depending on your system and how you're trying to configure it, it could potentially be used in lieu of ground source heat exchanger, depending on what you're doing. We're looking at it now at SUNY Binghamton. So I see Andy Jones here. It's something that he analyzed high level, and the idea, assuming that project continues to move forward, would be essentially an ambient loop with a bunch of air source heat pumps at the plant level, and then some water to water heat pumps at building level, and then you run your ambient loop at wherever it needs to be, 60 to 90 degrees or something on those lines. So while that's different than what we looked at for UMass, it's a way that you can add heating at a greater COP, especially when you drive that hot water supply temperature down. Be able to generate your heating via an electric means with a higher COP than, for example, an electric or electro boiler running at that COP of 1, or gas-fired equipment running, like Bill said, 80% or something on those lines, depending on technology that you use. So somewhere in the middle, it's kind of a happy medium at times, depending on the need and the client usage.
And then part of that, Alex, is that as we showed on the profile, we don't try to run it in the dead of winter. At least for this proposal, for this job, we only ran the heat pumps and the air source heat pumps in the shoulder period. So
Yeah, that's
this
really
is an overall flow diagram of what we proposed for the system at UMass Amherst. And to the right side is all the buildings, typical building connections. To the left is everything inside our plant, which they call the Energy Exchange Center, EEC. And then down here, this is a thermal storage tank we figured on that because we knew that was coming down the pike, working on the system. So, but to delve into one of the typical buildings, we had it arranged so that we were just basically adding we were serving buildings that were either standalone. They almost all had steam heat exchangers from a steam source here, but if they did have cooling, they had chillers in the building, or it was a mini district or something like that. So where there was a mini district, we just went to the building that distributed chilled water to those 3 or 4 buildings around it, and we just tied in like a parallel chiller here, and just treated it like building pumps. We delivered distribution pumps, delivered the water to the building edge, and then we have a deny valve, and we tie in just like you would tie in a satellite plant or something. Same for the steam system that ties in, except we did go in series on the steam here. We connect into the supply in, and then the return after that. So water flow is going that way. Sorry, return first and then supply. So we basically are running in parallel with the steam heat exchanger or the chiller. That helps with the phasing, because this wasn't all going to happen in one day. So you can go back and forth, do some testing, make changes, go back to your old chiller locally, and just it allowed them, a couple years if they wanted to, of transition back and forth until they got the whole new system up and running. Next slide jumps out the whole area. And if we jump over and focus on the plant, has 2 parts. So this is the initial part of the plant. The water comes back, hot water comes back at 110 here from the site. And the first thing we have it do is it hits our heat recovery chillers. That's these guys here, evaporators and condensers. So the hot side goes out from the condenser, and the cold side comes from the evaporator. And so we allow that those pieces of equipment which have harder time reaching the higher supply temperatures, let them see the coldest water, do what they can. It's a side stream arrangement, so it draws off what it can. We get as much energy out of this as the heat recovery will let us do, and that can be limited sometimes. As I said, we only have so many bores, so we can only get so much heat out of it. We also might be limited by how much simultaneous cooling we're doing if we're not going into the ground at that time. So there's a number of reasons why it's a good idea to just have this side stream, and it just adds heat to the flow as it goes by. And the chilled water works the same way. The 60-degree water comes back from the site here, and it gets side stream off to these the simultaneous cooling or ground source cooling heat recovery chillers, and then both of these pass on to the more conventional cooling and conventional heating systems that are further down in the plant, which is the next slide or 2. Here we go. So that we're moving down in the plant, and we just came from the heat recovery chillers. We came up, we did what we could with them, and now we draw off and we run through condensing boilers or heat exchangers using the steam from the cogen plant. And now we can send it out at 140 or higher if you wanted to in this configuration, back out to the buildings here. And then the one side on this, we put a sidecar connection here on the cold side when it's coming back. And that's because these are air source heat pumps. So they have trouble, as you said, Alex, it's 0 degrees outside. You might have trouble making 140-degree water. So we let them see the 110 degree coming back, and maybe they can only get it out to 120 or 130. But then we pass it on, and the heat recovery chillers can do the rest of it for them. So these are specifically arranged so that the warm water, the 110-degree water first hits air source, then ground source, and then the traditional, and get what you can and make up, when you haven't made it all, make up the difference with the traditional. And the chiller works the same way. You get what you can off the heat recovery chillers, and then we had traditional chillers because we don't have enough load out of the ground, so they add on what they need to do either in flow or in dropping the temperature a couple degrees. So and they're rejecting heat to those cooling towers like old style. And that's the way that works.
Great. Thanks, Bill. So before we jump to Q&A, I do want to ask you a little bit about projects and lessons learned. So maybe we spend the next couple of minutes just kind of walking through what you both learned on the project.
We did some test bores. We understood the ground properties, and you can see at the bottom left-hand star. So that's where we did our our initial test during our first phase, and then it was over their 500 million figure they thought they were going to use for the whole campus. And it just so happened up by the North Chiller plant, they had two buildings, one under construction and one renovation, and they were going to use standalone individual ground source heat exchanger systems. So they had their heat pumps involved, they had their ground source heat exchangers. Then as we were working on ours, the idea came up, said, okay, well, we have the North Chiller plant, we have some real estate there. There's a parking lot direct north or due north here, right above that CSL language where they said it's a flat parking lot. We know the ground properties. We did a test bore right there. We can get about what was it, Bill, 100 or 120 in there, something like that.
Yeah.
So we said we can get 120 in there or so. We can make a nice little loop. We can leverage the existing chiller bay that was open for a future chiller in the north plant, and we can make start a district ground source heat exchanger loop and low temperature hot water system to the north end of campus instead of to the southwest that we were originally looking at. Boom, there's the plant. Left a nice little bay to the figure on the left, one full chiller bay open that you could, in this case, slide some heat recovery chillers into. The full build out, like I was saying, it was planned for one more future cooling tower and one more future chiller, but of course the campus has evolved and planning changed over time.
Part of that was that we put in a thermal storage tank next to this, which we'll show you, but that allowed them to not install this fifth chiller.
Yeah, keep going, Bill, on this one.
So here's chiller number 4. Chiller number 5 was going to be here, but instead it is these two multi-stack heat recovery chillers in purple there, and we added pumps up above them, and basically it all fit in pretty nicely. So this was not planned to be extra space, but it was because we put a thermal storage tank outside that makes up the extra capacity the fifth chiller would have been providing for them. So now they were able, like Eric said, to co-locate the two heat recovery chiller ground source systems for the two buildings under construction in one location. It's bonus here because you're not limited. You're doing a lot of simultaneous heating and cooling. There's full-time winter load here. You got the thermal storage tank, so you can always dump chilled water into this district system, much more capacity than you would get out of the heat recovery chillers for just those two little buildings. So you couldn't do this campus wide, but it's a great opportunity for the first couple. They'll have great runtime for their simultaneous heating and cooling. And then so that's our plant. The heat recovery chillers are going to go here. This is the thermal storage tank that's under construction right now. And then long term is a future larger energy exchange center that'd be on the scale like a quarter or third of campus, like we did over for the phase 1 work. They call this phase 2, and you'd build that out in the future.
Awesome. Well, that brings us to the end of our presentation. So I will take this moment to thank you all for attending, and also thank Bill and Eric for sharing their case study about UMass Amherst. Please drop your questions in the chat. I will read them off in a second. So with that, we have 2 questions in the chat right now. So the first one goes back to my question about COP. And Paul asks, how does the COP compare relative to the different energy costs? And while you two are answering that, Paul, I will open it up so you can speak and you can have some back and forth dialogue as well.
Yeah, Paul, I mean, that it's true. We talk only about energy and we're using less energy units, but the electric energy units cost a lot more than the gas and oil energy units. So all these things, this client, when we did the analysis for that phase 2, where they were combining the two buildings, heat recovery chillers into one location, and at one point they said, "What's the payback on this?" And said, "There's no payback on this." So when you take into account how much gas costs today, how much electric costs up there, it is not an energy savings. Even though your COP is 3, 4, 5 times better, depending on your energy costs, but today's rates, New England, it's still cheaper to go with gas. The condensing boiler's the cheapest way to go.
Thank you. I sense that based on how you addressed it earlier on in the presentation there, that there's really a net zero difference between conventional and the new technology.
Yeah.
And would you say,
Thank
Bill,
you.
that it's not necessarily the cost of energy that's driving this change for campus? It's their carbon reduction goals and trying to reduce
Right.
their.
That's
Sure.
what it's all
Understood.
about. Yeah.
Cool.
Understood.
So the next question comes from James, which is, would you have made sense to avoid some of the marginal capital costs, talking about 120 to 100 or 140 to 110, if you had a larger delta T on the 120 to 100 option? So going from 120 to 90 or 130 to 100. And James, I will also open it up for you to speak.
Yes. Eric, you want to take it or you want me to take it? So you're
Go
right,
ahead.
Jim.
Good.
You're right. It's the delta T that matters, not the temperature so much. We just felt that going down to 110, I mean, going below 100 was a little bit pushing it for these old systems. But if once you got into it and looked on a building by building basis, maybe you could get away from that. But you have to do it at all the buildings. It has to work for all the buildings if you're going to settle on that. But that's true. It's the delta T, not the temperature, that matters.
And when
The
you
other thing
say
I
old
forgot to mention.
systems,
Yeah, go ahead.
when you say old systems, you mean the building systems.
Yeah,
Okay.
yeah, and that is the other thing is some of these, they had a mix of 20 and 30 degree delta T systems on their different buildings. If you have a 20 degree delta T system and you give it 30 degree delta T new district heating, you're going to be able to save the piping. You're probably not going to be able to save the equipment, but you probably never would. But you do save the piping. If you have a 30 degree delta T system in a building and you bring district heating at 20 degree delta T, you're going to have the pipe's probably not going to be big enough. So you're going to replace the pipe in addition to all the coils and various air handlers and stuff, fin tube.
Well, I appreciate the both of you, Eric and Bill. Kudos to you for all your hard work at UMass Amherst, and look forward to our next decarb debrief session in March. So thank you all for our attendees, and I will sign us off and have a great afternoon. Stay warm, everyone.